Okay, hello everybody. Thanks for taking the time to watch this video today. We are going to begin our discussion in Chapter 2, Section 2. And what this chapter and section covers are functions. Now, you may have learned some of this stuff before, so hopefully it's not too terribly difficult for you. So this is what we're going to be talking about in Chapter 2, Section 2. We're going to talk about determining whether relations between two variables are functions, and then use function notation. We're going to find the domains of functions, and then we're going to use functions to model and solve real-life problems, and we're going to evaluate the difference quotients. So the first thing we're going to discuss is an introduction to functions and function notation. So a while back, I don't know how many years ago it would have been now, you learned what function notation was. And it's simply a replacement for notation that you used prior to function notation. So if we had this function y equals 2x plus 1, what we did is we chose with function notation to replace the y with f of x equals 2x plus 1. Now what that does, it looks like it might be a little bit more confusing, but what it does is it allows us to know what number was put into the function, so we know what number was put in that gives us the output. Okay, that was not worded very good. Let me try this again. So what function notation allows us to do is to know what number is put into the function and then what output is paired with that input. So as an example, if I wanted to put the number 3 in, I would just write y equals 2, 3 plus 1. I'd get 6 plus 1, and I would just get y equals 7. So if we just had y equals 7, that does not tell us anything about what number was put into the function to get that output. But if you use function notation, you would have f of 3 equals 2 times 3 plus 1. So f of 3 equals 6 plus 1. F of 3 equals 7. Now looking at this notation, you can see that we plugged in the number 3 into the function, and then the output that we got was 7. So it's a much more descriptive way of writing functions. That's why we use it in upper level math. Now, something to keep in mind with functions, and you probably have already previously discussed this, is functions have what are called a domain and a range. And the domains are simply the numbers that are allowed to be put in for the x value. So whatever you put in for x is considered the domain. The ranges are going to be what we get as outputs after we put the domains in. So they're the f of x values, or also known as the y values. So these are your domains, and then these are your ranges. Each of those are listed in set notation, or you can have them as mappings, as you see here. And what this is showing you, this is a mapping that shows you each number in the domain, which is over here, and what number it's paired with in the range. And what you can see, there's an arrow drawn from each x over to each y. Now, where we run into trouble and where something can fail to be a function is if an x would split and go to two y's. And I'll explain why that is in a second. But remember, not all relations are functions. So relation is a general term that maps one number to another number. If it follows a certain set of rules, it can then be considered a function. So in this case, what we are looking in a mapping is if an x value would split. So if you saw the 4 go to the 9 as well as the 15, this would fail to be a function. So as we look over this entire domain, none of the domains are pointing to two different y's. So this would be a function. So the following ordered pairs can represent this function. The first coordinate, x value, is the input, and the second coordinate, the y value, is the output. And again, the x values are your domains, and the y values are your ranges. And what I want you to notice is there is no repeated x anywhere. Okay, that is one of the keys to something being a function. You cannot have a repeated x. If the x is the same and the y's are different, it would fail to be a function. And that's what this box is saying. Characteristics of a function from a set A to a set B. Each element in A must be matched with an element in B. Some elements in B may not be matched with any element in A. So every x over here has a pair. That's the first thing. The second thing, not every y has a pair. That's okay. The third thing that it says is two or more elements in A may be matched with the same element in B. So they're saying you can have 4 go to 15 and you can have 3 to go to 15. That's okay. If two x's go to the same y, that's perfectly fine. But number 4 says an element in A domain cannot be matched with two different elements in B. And that's where I was saying 4 cannot split like this and go to 13 and 15. If it did that, that would fail to be a function. Now there's 4 ways to represent a function. We can represent it verbally, numerically, graphically, or algebraically. And I'm going to show you a couple of those here. Okay, so let's take a look at this example one. We have 3 different scenarios here that we got to take a look at and determine whether it is a function. So the directions say determine whether the relation represents y as a function of x. The first one says the input value x is the number of representatives from a state, and the output value y is the number of senators. Okay, so what we would have to do is know each of the representatives from each state. I do not know that offhand, but those numbers will vary based on the population of each state. But the output value is the number of senators from each state. And in this case, the number of senators in our country is always 2. That is set. So no matter what the input value would be, any number of representatives, the output value would always be 2. And so what you would have is you would have a scenario, and I'm just going to make some numbers up. So we could have like 5, we could have like 3 or 7. All of those numbers are always going to be pared down to 2 like that, because there's only ever 2 senators from the state. So therefore, yes, this would be a function. Looking at B, they give us the inputs, they give us the outputs. Remember, the inputs are your domains, the outputs are your ranges. Okay. And what we're always looking for is we are looking for any repeated x values. And as you can see, there is a repeated x value right here. There's 2, which goes to 11, and 2 also goes to 10. If that happens, then the answer would be no. This is not a function because there is a repeated x value. Okay. Now the third one, there is another test, and you may or may not have learned this before, but it is called the vertical line test. And what the vertical line test allows us to do is to very quickly look at a graph and determine whether that graph would be a function. And so you just take and you pass a vertical line through the entire graph. I'm doing multiple lines just so you can understand. And you look to see if that vertical line at any time intersects more than one place of the graph at a time. In this case, it does not. So this would pass and would be a function. So this would be yes. Now, as an example, if I were to show you one where it would not, if I put a dot right here, let's put a dot right there, okay? And then let's pass a vertical line through there. And what you're going to see is it intersects in 2 places. If we had a graph that looked like this would actually be no. Now, why would it be no? Well, let me show you. If I wrote the ordered pairs of these, this would be -2, 3, and then this one would be -2, 0. What I want you to see is the x are repeating, just like we had over here. If you get a repeated x, it is not a function. It would fail to be a function. So that's really important to remember. And there's multiple ways to do it. You could look at the table. You could look at the graph and use the vertical line test. You could also look at ordered pairs, depending on how they give us the functions. Okay, so the next example that I want to show you is how we use function notation to evaluate. And let me fast forward here. So function notation and why that's important is what you see right here. So when they tell us what they want us to substitute in for x, you can see that instead of having f of x, we have f of -1. And what that's telling us is inside our function f, we should put the number -1. And then you, of course, follow PEMDAS after that to simplify to get your output. And you can see that if we have f of -1, the output was 5. And so it allows us to see what the input was and then what the output was. Same thing here. We plugged in 0, so we found f of 0. And when we did that, the output was 3. The last one is f of 2. And following PEMDAS, substituting 2 in, following PEMDAS, you can see we got -1. So again, function notation allows us to very easily see what the input and then the output were from the function. Thing to keep in mind about function notation is they can use various letters to name functions. We can call functions f. This particular function is called f. Here's another one. It's called f, but notice they changed it. So instead of having f of x, they had f of t. They tend to use t for time or temperature a lot of times in word problems, which is where you'll see the x get substituted and get a t put in for it. They also can name a function g or h. So the actual first letter is an indicator of the uniqueness of the function. So they don't like to use f for multiple functions. They'll use f and then g and then h to delineate between which function they're referring to. And you can use s and whatever else variable you want. As a general rule, they tend to use the letters around f, g, and h as the function names, and then they tend to use the letters at the end of the alphabet for the actual variables you're going to substitute in for. So in other words, X and Y and Z and S and R, they'll use those, and T tend to be the variables. And then the function names tend to be letters at the beginning of the alphabet. Now, the next thing that I need to introduce to you is what a piecewise defined function is. Now, some teachers call these split domain functions because they have a split in their domain. But as a general rule, your books and most of your teachers will call these piecewise defined functions, as I will. Now, what a piecewise defined function is it is pieces of two or more individual functions put together. And the best way that I can describe this is if you think of like maybe you did a collage for a certain class, maybe it was an art class or even a history class where you had to make a poster or something, where you cut various aspects of a magazine out and then put them together into one poster to prove a point. That's kind of like what this is. A piecewise defined function cuts pieces of individual graphs and then puts them together into one graph. So it's kind of like a Frankenstein graph. So what I want you to see is how these work. So you don't normally have to go to this extent to graph it, but I want to show you what a piecewise defined function, how it's put together. So if we look at this first part, you can see this is f of x, and then it gives us this bracket, and it says f of x is actually two different parts. It's x squared plus 1 when x is less than 0, and then it's x minus 1 when x is greater than or equal to 0. So they want us to evaluate this function. Now, to know which part here that we put our x's in, you have to follow the domain restrictions. Okay, so here's what's important to understand about this. This part right here, x squared plus 1, is only to be used when you have an x that is less than 0. So if your number is -1, -2, -3, -0.5, any of those numbers that are smaller than 0, you will put it into here. If the number that you have is greater than or equal to 0, you will put it into this part of the piecewise defined function. And so looking at our x values, we're going to start with x equals -1. So we have to determine which of these two does -1 belong to. -1 is less than 0, which means we're going to put -1 into this piece. You do not put it in both pieces. You only put it in one piece, whichever part it qualifies for. So to do f of -1, that is equal to -1 squared plus 1. Again, I'm putting -1 in here because -1 is less than or equal to 0. And then you simply follow PEMDAS. So f of -1 would be 2. Right? The next number they want us to plug in is 0. So once again, you have to determine which part do I put in 0, the first part or the second part. And that's completely based on what these are. And in this case, 0 is greater than or equal to 0. So we're going to put that into the second part. F of 0 is equal to 0 minus 1. So f of 0 is equal to -1. Now the last one right here, we have +1. And once again, you have to determine which part of the piecewise defined function it goes into. +1 is greater than or equal to 0. So once again, +1 is going to go into that. So I'm going to do f of 1 equals 1 minus 1. F of 1 is equal to 0. So right here, here, and here are our three outputs. And again, what's nice about function notation is we can see exactly what number was put into the function to know how we got that output. Now, the domain of a function can be described explicitly or it can be implied by expression used to define the function. And so an implied domain is the set of all real numbers for which the expression is defined. For instance, the function f of x equals 1 over x squared minus 4 has an implied domain consisting of all real numbers x other than +2 and -2. Here's why this has an implied domain and why you need to be aware of when you have functions, what numbers are okay and not okay to put in. In this class, you will have two instances, two types of functions that will give you a restricted domain. The first type of restricted domain function you're going to have is what you see in front of you, where you have a variable on the bottom of a fraction. Thing to keep in mind, if you have a fraction, you are not allowed to have 0 on the bottom. So if you have a function that has a variable on the bottom, you need to determine what numbers would make that bottom 0 and then eliminate them from the domain. So in this case, if I would take this number right here, this x squared minus 4, and I set that equal to 0 and I solve it, you can see that the number 2 or -2 would make the bottom 0 if I plugged it in. Therefore, we have to restrict our domain to exclude the numbers 2 and -2. The other type of function that you will get a domain restriction is going to be a function like this, where you have a square root of a variable. Keep in mind that you are not allowed to square root negative numbers. So the domain for this particular function, or I should say the domain restriction, is x cannot be less than 0. So x has to be greater than or equal to 0 because you're not allowed to square root negative numbers. So those are the two types of functions in this class, this entire year, that you will ever have a domain restriction in. Ones that have a variable on the bottom of a fraction, and then ones that have a square root. So this particular example asks you to find the domain of each function. So it's very simple. You're simply going to list, if you have ordered pairs, all of the x values. So let me show you how you do that. You do a squiggly bracket, and then you just list the x values. So that's the domain for the first one. Now for the second one, you can see we need to determine what x value is not allowed to be put in there. And in this case, if I take x plus 5 and I set it equal to 0, X cannot be -5. So it would be all real numbers except X equals -5. Okay? Now for part C, for part C, you can see we have a function that gives us the volume of a sphere. Now remember, the domain are the inputs. And think about what R stands for. R stands for radius. So if we did not have a radius that was positive, then it wouldn't make sense and you wouldn't have a sphere. So the domain for this is the radius needs to be greater than 0. Now the last one here is a square root. So remember, I said the two main places you're going to have domain restrictions are functions that have variables in the bottom or square roots. And the way that we do this is you take whatever's under the square root and you set it greater than or equal to 0 to get your domain, because whatever's under there has to be 0 or larger so we can square root it. So we set 4 minus 3x greater than or equal to 0. I'm going to subtract 4 from both sides first. So I have negative 3x is greater than or equal to negative 4. And I'm going to divide by negative 3. And when I do that, I get x, don't forget to flip over the inequality sign, x is less than or equal to 4/3. So the domain would be this. You have to pick x's that are less than or equal to 4/3. All right, that's what I have for you today. Thanks for watching, and please complete these homework problems, and I will go over them with you tomorrow. Have a great day.